Greetings all. My name is Zinzipho Shaqatai, and I'll be presenting on chapter 5. What kind of science is physical geography? Before we ask what kind of science physical geography is, it is worth reminding ourselves what we might mean by the term science in the first place. So there is more than one kind of science, or there are many different ways of pursuing scientific inquiry. Science has been a remarkably successful set of tools to explore the workings of the world and the universe. Despite those who argue that it is only one of many equally valid ways to establish the truth, science has touched all parts of human life and provides a stable ruling paradigm whose aspirations and devices, such as objectivity, while contested, have constructed a most powerful understanding of nature. To be a science is crucial for physical geography because it embeds the discipline into a string of different scientific disciplines. As a result, it would be difficult for an academic subject to claim objective understandings of nature if that subject weren't in some way able to call itself scientific. A naive view of science often assumes that it must contain a significant component of laboratory work where accurate and replicable measurements are made of the system, and where we try to verify statements or hypotheses. Replicable measurements are made when the apparatus is controlled and extraneous noise is minimized. In principle, therefore, an experiment conducted in one part of the world should be exactly replicable in another. In this view, we might see the hard physical sciences, for example chemistry and physics, as living up to this ideal, and we would relegate field-based subjects such as physical geography, ecology, and geology, in which replicable measurements often cannot be made, to the realm of non-science. However, there are many different ways in which we can try to define science, and as we will see in the next slides, all of them have problems. So the three main ways to define science. Number one, science is an organized body of knowledge where objects are classified into significant types or kinds. For example, we have taxonomy. Science is a way in which we seek to describe, explain, and maybe predict the conditions under which events in the human or natural worlds occur. Science is the development of explanatory principles by which a large number of propositions help us to construct a logically unified body of knowledge. Such an approach is sometimes deductive, where one statement may be said to follow from others as a consequence of reasoning from general theories to specific instances. Then we have testability and falsifiability. For some commentators, the ideas of testability and falsifiability are often cited as being crucial attributes of scientific practice. So a testable statement can be determined to be either true or false by making observations about the world. One version of this is verifiability. Can a statement be supported by observations? But a more widely supported version, at least among philosophers of science, if not practitioners, is falsifiability. So falsifiability, according to philosopher of science Karl Popper, it is sometimes seen as the bedrock upon which science rests and the way in which science and non-science can be distinguished. It argues that the aim of scientific testing is to refute a hypothesis, not seek evidence to support it. The process of science starts when an observation is capable of contradicting an existing theory. Once this happens, the theory is open to rejection, such that a new one is proposed or the existing one modified. And the logical consequences of this new or modified theory are once more subject to empirical testing. For some commentators, it is easier to describe what science is not. For some, it is not an investigative procedure to be followed mechanically and rigidly. So now we will look at Ernest Nagel's take on defining science. As the philosopher of science Ernest Nagel says, there are no rules of discovery and invention in science any more than there are any rules in the arts. We should be prepared to say that the consequences of the scientific endeavor have been sufficiently impressive to make the set of practices which can be described as science more useful and superior to alternatives to it. So now we have the ordered list of science. An ordered list of the sciences usually places physics at the head and subjects like psychology and ecology near the base. So as you can see on the pyramid on the right, it places physics at the top of the pyramid, and then we have chemistry followed by biology, then we have psychology. But on what basis is this distinction made? So arguments based on the ordered list of science. Some argue that the list of sciences starts with physics because of its closeness to the purity of formal logic and mathematics. Some argue that the list of sciences starts with physics because of its closeness to the purity of formal logic and mathematics. Much of physics can be described in the language of mathematics and by the necessary truths of formal logic. Others argue that certain types of physics offer the best exemplars of the relationships between cause and effect. Right. The ordered list of science shows that science is a mixed set of subjects. There are important differences between subjects such as physics and ecology, which are at the opposite ends of our spectrum as seen in the pyramid. Physics basically deals with irreplicable measurements carried out under laboratory conditions. Here, the variables under analysis can be isolated, investigated, and tested. Ecology, on the other hand, is dominated by complexity associated with contingent conditions, multivariate system parameters, and issues such as scale problems, nonlinearity, and emergent phenomena. And we will discuss the emergent strategy later on in the slides. So what is physical geography? For physical geographers, being scientific matters. It means that they can engage in debates with other natural sciences, they can use their methods and their philosophies, and they can share their motivations. If physical geography is not regarded as a science, then its status is lessened. So what is physical geography? Physical geography is the study of the natural elements that constitute landscapes. It is concerned with landforms, soils, biological elements, and the effects of climate and weather. Physical geography looks at the natural processes of the earth, such as climate and plate tectonics. Areas included in physical geography, the subdivisions of physical geography include hydrology, we have glaciology, biogeography, climatology, landscape ecology, and geomatics, just to list a few. To define or understand physical geography as science, we need to understand geomorphology, because in this chapter, we will explore different ways of science inquiries with particular reference to geomorphology. So geomorphology is the study of the shape of the Earth's surface, and how it came about. Geomorphology can be viewed as forming the core of physical geography. Geomorphology, allied to geology, played a crucial early role in constructing models of landscape evolution. Other physical geology subdivisions were given less importance. What kind of science is physical geography? So physical geography can sometimes be seen to be synonymous with geomorphology. Most geography departments in Britain and North America will have one or more geomorphologists in their complement of physical geography academic staff. Some will have hydrologists. One way to grasp the different meanings of science is by examining how a discipline has changed over time. Geomorphology has changed from a pre-scientific purely descriptive subject to a historical science that was concerned with evolutionary change. It further on evolved to a science based upon detailed descriptions of processes using the laws of Newtonian mechanics. An example will be the evidence that was employed by Louis Agassiz in 1837 to suggest the operation of continental scale glaciations in shaping the landscape of of the northern hemisphere. In the mid-19th century, physical geography and geology were used systematically to interpret landscapes and develop models to understand landscape change. In this context, W. M. Davis is often seen as the founder of pre-World War II Anglo-American geomorphology. He puts emphasis on a large-scale historical and evolutionary approach to landscape evolution, and his work was published at the end of the 19th century. Other workers like G. K. Gilbert used the language and methods of physics, mechanics, and engineering to develop alternative schemes. Davis stressed three important themes. His approach was regional and employed the drainage basin as the fundamental geomorphic unit. He stressed the nature of change over long-term geological timescales. He was particularly influenced by Hutton's theory of gradualism in understanding landscape change and by Darwin's evolutionary theories. He argues that landscapes could be characterized as moving through a succession of characteristic states, where we have the youth, maturity, and old age. Davis's work was widely criticized. However, this led to alternative methods of geomorphological understanding being constructed. So the main criticism were focused on Davis's epistemology. His schemes were excessively evolutionary and theoretical. His theories lacked a solid grounding in field observation and experiment. His theories lacked the empirical base. Analysis of landscape change did not produce testable hypotheses. Davis also fell foul of the Popperian criterion for falsifiability as a mark of a science, and his theories were qualitative and descriptive and of ignoring process. The qualitative revolution of physical geography between the 1950s and 1960s. So from the mid-20th century onwards, the introduction of computers and powerful statistical models allied to logical positivist philosophers of science have allowed physical geographers and allied earth scientists to construct a new physical geography based on systems theory and on the language of mathematics and physics. Revolution was an attempt to recognize and simplify the complexity of natural systems by modeling them as the result of transfers and storage of mass and energy. These approaches have created the dominant physical geography paradigm in British and American universities, often referred to simply as the process of form paradigm. This physical geography has involved detailed studies of processes, often on a small scale, allied to sophisticated laboratory and field experiments, statistical treatment of the results, and the application of computer modeling. The aim has been to understand the complexities at small spatial and temporal scales and to extrapolate this knowledge to explain change at the landscape scale, which is obviously large. Moving on, we look at reductionism, emergence, and complexity. Small-scale processes knowledge gained from Newtonian classical mechanics may be viewed as historical in that the equations describing the processes do not have a time dimension within them. We wish to obtain an understanding of large-scale landscapes and landform development. In this case, the processes are historical, where the landscape is seen as being created by the accumulation of processes over time, operating on varying materials, possessing varying properties. At the landscape scale, the predominant process of form paradigm therefore aims to create explanations via what we might call, number one, reductionist methodology, and then later on we have the emergence strategy. The emergent strategy. So with the reductionist methodology, it looks at the purpose basically of the reductionist methodology is that it looks at understandings at the small scale, right? Whereby understandings at the small scale are extrapolated upwards to provide explanations at the large scale. It also argues that understanding of complex systems can be gained by examining the component parts of the system, and this is reductionism. The reductionist methodology has two strains. One, we have ontological reductionism, and we have epistemological reductionism. So ontological reductionism argues that all that exists are the fundamental constituents of matter or entities that are determined by them. With epistemological reductionism arguing that theories and conceptions about macroscopic entities can be reduced to theories about fundamental concepts. With the reductionist methodology, we have criticism, right? Where quantum mechanics shows us that the reductionist program is logically flawed, perhaps practically flawed as well. Reductionism provides us with analysis rather than synthesis of complex systems. Diech sums up the shortcomings of reductionism by suggesting that it misinterprets the structure of scientific knowledge. The physicist Anderson argued that the reductionist hypothesis may still be a topic for controversy among philosophers, but among the great majority of active scientists, it is accepted without question. Moving on, we have the emergent approach. Alternative schemes stressed the emergent properties of landscapes. Others have suggested that explanation is scale dependent, in that our best understandings follow from the examination of parts of complex systems at the scale at which we are interested. So this is the emergent strategy. Emergence argues that explanation depends on scale. A plurality of theories may provide the deepest understanding. So this brings us to nonlinearity and complexity. So in order for us to understand the reductionist approach and the emergent strategy in depth, we have to look at nonlinearity and complexity. The landscape, which many physical geographers study, is a very much more complex set of systems than the early positivist quantitative practitioners expected. So the landscape is driven by processes which are in the main nonlinear, and this obscures cause and effect relationships. Nonlinear systems are those whose causal powers are not derivable from the aggregations of lower level behavior, since these cannot be known. It may be that all cases of nonlinearity are emergent. The specification of the initial conditions of a system is not possible. This leads to the problem of equifinality, whereby a landform or landscape may be created by a number of different processes operating at different times, together and individually. For example, we look at the nature of the granite tors of Dartmoor. This has alerted some physical geographers that the way to treat such systems is to understand emergence. A physical geography based upon the principles of emergence would therefore recognize that the relations between objects plays a special role in the landscape, and that landscape form is contingent upon a number of influences which may not be amendable to reductionist explanations. So in conclusion, when we answer what kind of science is physical, what kind of science is physical geography? Physical geography is a complex science comprising a collection of related subjects whose methodologies and foci of attention straddle the ranges of science. In geomorphology alone, there is a range from small-scale studies employing classical mechanics and stochastic interpretations of process to large-scale narratives dominated by ideas of contingency, equifinality, and nonlinearity. Harrison believes that we should see this range of approaches as a strength, and some researchers have contested that the greatest challenge facing physical geographers can be found here. They believe that developing methodologies that can bridge the scales is both achievable and desirable. In conclusion, the reductionist and emergent approaches therefore provide us with complementary rather than competing descriptions of landscape change. The future challenge of physical geographers may be to prescribe these approaches in greater detail and to recognize that the subject, and in science general, is like a commonwealth of knowledges, not an empire. And we have our questions. So question 1, what are the 3 ways to define science and what makes physical geography a scientific discipline? Question number 2, what are the 2 versions of testability? And lastly, compare the reductionist methodology to the emergent strategy. Thank you.